For decades, we've been told that black holes are the ultimate cosmic monsters. Infinite pits of despair where gravity destroys everything, even light. But what if there is something out there even more terrifying? An object that doesn't just trap you, but actively, violently rejects the laws of physics. Meet the Gravistar. From the outside, it looks exactly like a black hole. But if you were to fall toward it, you wouldn't slide into a dark abyss. Instead, you would slam into a hyperdense, vibrating shield of exotic matter that would instantly obliterate your atoms. Scientists are beginning to realize that our universe might be hiding an entirely new class of cosmic killers. And it's not just about space, it's about the laws of physics themselves. To understand this, we need to start with how a black hole forms. When a very large star reaches the end of its life, it runs out of fuel. For most of its life, a star is balanced. Gravity pulls it inward, and energy from nuclear reactions pushes outward. But when the fuel runs out, that balance ends. Gravity takes over. The star begins to collapse. If the star is large enough, this collapse cannot be stopped. The core is squeezed smaller and smaller. Density increases without limit. According to Einstein's theory of general relativity, this process creates a black hole. At the center of this object, theory predicts something called a singularity. This is a point where matter is compressed into infinite density. And at this point, our laws of physics no longer work. Time and space lose their normal meaning. And this is where the problem begins. In science, infinity is usually a warning sign. It often means that a theory is being pushed too far. It suggests that something is missing. For some scientists, the idea of a singularity is not a real physical object. It is a sign that our current understanding is incomplete. In the early 2000s, two physicists began to explore this idea in a different way. Pawel Mazur and Emil Mottola asked a simple question. What if a collapsing star never actually forms a singularity? What if something stops the collapse before it reaches that point? From this question, a new idea was developed. They called it a Gravastar, short for gravitational vacuum star. In this model, a star still collapses under gravity, but instead of forming a singularity, something different happens. At a very small scale, the collapse changes state. The material does not continue inward forever. Instead, it transforms. Inside a Gravistar, the rules of reality completely shift. Instead of a crushing point of infinite density, the center is filled with a bizarre concentrated bubble of vacuum energy. This is the exact same dark energy that is currently forcing our universe to expand. Holding this volatile cosmic balloon together is a razor-thin outer shell made of exotic matter. This isn't normal matter like the atoms in your body. It possesses negative pressure, meaning it violently pushes outward, fighting against the crushing weight of gravity. This is not normal matter like we see on Earth. It has unusual physical properties and behaves differently under pressure and gravity. Together, the shell and the inner region form a stable object. From far away, a Gravistar would look almost identical to a black hole. It would have strong gravity. It would bend light. It would pull in nearby gas and dust. Even with powerful telescopes, it would be very difficult to tell the difference. But inside, it is very different. There is no singularity. There is no point where density becomes infinite. Instead, there is a vacuum-like interior surrounded by a thin shell of matter. This difference may seem small, but it changes everything. In the standard black hole model, there is something called an event horizon. This is the boundary around the black hole. Once anything crosses this boundary, it cannot return. Not even light can escape. This creates a major problem in physics. Think of it this way. According to the fundamental laws of quantum mechanics, information can never be truly destroyed. If you burn a book, the ash and smoke still contain the quantum data of the words. But if you throw that book into a black hole, that data is permanently deleted from the universe. This breaks the laws of physics, creating a nightmare scenario known as the information paradox. A Gravistar fixes this. Because it has a solid physical shell instead of an empty event horizon, anything that hits it gets scrambled and preserved on the surface, meaning the universe's data remains safe even if the traveler is vaporized. It's one of the biggest unsolved problems in physics. Gravastars offer a possible solution. In a gravistar, there is no true event horizon in the same way. Instead, there is a physical shell. When matter falls toward it, it doesn't disappear into nothing, it interacts with the shell. In theory, the information could be stored or preserved in some form. This means nothing is truly lost. So, gravastars do not just replace black holes, they also solve a problem that black holes create. They allow quantum mechanics and gravity to work together without contradiction. This is one of the main reasons scientists study the idea. Now let us look more closely at the structure of a gravistar. The shell is extremely thin. In theory, it is incredibly dense. All the mass of the object is contained in this very thin layer. This shell is held in place by the balance between gravity pulling inward and exotic matter pushing outward. Exotic matter is important in this model. It behaves differently from normal matter. Instead of resisting compression in the usual way, it can create what is called negative pressure. This means it pushes outward. This outward force helps support the structure and prevents collapse. Without it, the gravistar would not be stable. Inside, the vacuum energy pushes outward as well, balancing the system. In this way, a gravistar is not just a collapsed object. It is a carefully balanced structure. However, exotic material is still theoretical. It has not been observed in large amounts. Some small effects in quantum physics suggest it could exist, but nothing close to what would be needed to build a gravistar has been found. This makes the idea interesting, but still uncertain. One of the biggest challenges in studying gravastars is that they are extremely difficult to detect. From far away, they look almost exactly like black holes. For example, in 2019, scientists released the first image of a black hole's shadow in a galaxy called Messier 87. It showed a dark center surrounded by a glowing ring of hot gas. A gravistar would likely produce a very similar image, the same bending of light, the same bright ring of material. So imaging alone may not be enough to tell them apart. Because of this, scientists look for other signs. One possible method is gravitational waves. These are ripples in space and time that are created when massive objects move or collide. They were first detected in 2015. When two black holes merge, they produce a clear signal that fades in a specific pattern as the final object settles. If gravastars exist, their signals might be slightly different. Because they have a physical surface instead of an event horizon, some of the gravitational waves might reflect off the shell. This could create small repeating signals after the main event. These are sometimes called echoes. So far, scientists have searched for these echoes, but the results are not clear. The signals are very weak and the data is difficult to interpret. Future observatories may help solve this. New detectors will be more sensitive and may be able to pick up clearer signals from distant cosmic events. If they do, they could confirm whether gravastars exist or not. This brings us to an important question. Could objects like this already exist in the universe? At the center of our own galaxy sits an object called Sagittarius A. It has a mass about 4 million times that of our Sun. We cannot see it directly, but we can observe how stars move around it. Those observations strongly suggest a supermassive black hole. But from a distance, a gravistar could behave in almost exactly the same way. So at the moment, both ideas remain possible. We simply do not yet have enough information to be certain. If gravastars do exist, they would change how we understand the universe. Objects we once thought were points of no return might actually be structured systems. Instead of destroying information, they could preserve it. Instead of ending physics, they might connect different parts of it. They could even play a role in the larger structure of the universe itself, since the vacuum energy inside gravastars is similar to the energy thought to drive cosmic expansion. For now, gravastars remain a theory. They exist in equations, models, and scientific discussion, but they have not been proven, and they have not been ruled out. This is what makes them important. Because in science, the biggest discoveries often begin as questions. And sometimes those questions begin by asking whether what we think we know is actually complete. Black holes may not be the final answer. They may simply be part of a bigger story we are still learning to understand.